Sorry for the inconvenience, but thank you very much for supporting this remote presentation. I appreciate your time and the support. And my name is Xinfeng Gao. I am a professor of mechanical and aerospace engineering from the University of Virginia. Today, I'm going to share and discuss a new quantum algorithm to approximate the nonlinear terms in Navier-Stokes equations. I will focus on the concepts, and then we will basically go through some specific steps, and I will explain this long-term goal. We actually interested in developing utilizable algorithms for quantum computing fluid dynamics problems at a high Reynolds number. So I'm interested in high Reynolds number because a lot of applications are involved, relatively high Reynolds number. They feature strong and complex nonlinear interscale interactions between velocity components and space-time locations. So it's very important to efficiently compute these interscale correlations. Now, when we model and simulate a practical high Reynolds number turbulence on classic computing, and it's very challenging. As we know, turbulence is an older problem, but we need a new solution. Can we harness the vast parallelism and the entanglement that the quantum computing technology can offer, so we can enable the direct numerical simulation of high Reynolds number turbulence on quantum computer that we can still not achieve today on the classical high-performance computing system, particularly in terms of the computational speed, resource efficiency, and solution accuracy. And then I will focus on the concepts, and then my three previous speakers did a wonderful job, so they laid out the ground, a lot of terminologies I can skip into the detail. So the long-term goal, as I said, I'm interested in practical algorithm for high turbulence, high Reynolds number turbulence flow. But the critical challenge is addressing these nonlinear terms. We have a lot of packages and how to solve linear system, linearize the nonlinear terms. But can we actually address the nonlinear terms directly? So this is my interest. Can we first tackle the nonlinear term? It is really representative for many partial differential equations governing this fluid dynamics problem. So this is the core term I am focusing on. So the specific objective is how do we efficiently represent, encode, process, evolve these nonlinear terms on the quantum computer. So the new algorithm, we have three steps, and this is constructed based on matrix product states and a matrix product operators. Now, I would just first go through these three steps, and we come back to explain what's new about this method. What is the challenge of this method? How do we address these potential challenges? So the first step is we construct a multi-resolution. So the keyword here is multi-resolution, Schmidt decomposition on a composite grid. So this omega L is a composite grid. So you see this figure here. Essentially, I have a AMR grid, adaptive mesh refinement with two-level refinement. Omega 0 is the coarse level. This is the intermediate level. This is the fine level. Just use the two-level refinement as an example. And also this AMR grid has a time refinement. You have a subcycling. So basically space-time refinement. I call this the composite grids because later I also want to mention the graph. So there's a graph here. The graph, you have this connection between these black dots, the red dots, and the green dots. So graph. So overall, collectively call this a composite grid. So first, we want to construct a multi-resolution Schmidt decomposition, and then secondly, instead of linearize all the terms, so what we do is trying to combine the unitaries linearly to create the quantum nonlinear processing unit. So using this MPS and MPO. So this is working for one solution variable, but our system typically involves multi-variables. Then we have to expand the algorithm for multiple solution variables. Now, by design, this algorithm features distinct computational efficiency and solution accuracy. The reason I claim that efficiency, computational efficiency and solution accuracy is that when you do Schmidt decomposition on a grid has different resolution, is faster than a uniform grid. Imagine you have uniform grid everywhere, omega 2. But that's obvious, we know when we do adaptive mesh refinement. But what's the solution actually coming from? In fact, this is very interesting, supporting the turbulence nature. The space-time interscale correlation benefit from different resolution. So if you take this 3 grid, you compute this correlation between any 2 level of resolution, it gives you higher accuracy. So this is the 2 features, computational efficiency and solution accuracy. So this is essentially that we want to integrate our AMR and the graph, allowing these interscale correlations to be computed more efficiently and more accurately. So this is a novelty of this adaptive Schmidt decomposition. So what is the process? So the process that we perform Schmidt expansion on this composite grid, and then this is representing the velocity, and this is the Schmidt decomposition coefficients. I'm not going to discuss each term, and you probably are already familiar with the Schmidt expansion. And also I found that for the mathematical terms, equation discussion is more constructive when we have questions. So at this point on this slide, we'll just focus on the procedures. And then if you have questions, we can come back. How do we compute each term and what do they mean? So we perform the Schmidt expansion on a composite grid. Then we apply MPS for quantum embedding for flow variables. Once you have this MPS, and then we can linearly combine our unitary to get the nonlinear quantum compute processing unit. So we will finally test the accuracy of the multi-resolution space correlation for these nonlinear terms. So the idea is to compare the accuracy with this linear. If you linearize the nonlinear terms, we have linear solver, we linearize nonlinear terms, get a solution compared to this direct calculation through the multi-resolution scale correlation. So before we go on for this quantum nonlinear processing unit, I mentioned that the new feature is the computational efficiency and the solution accuracy. But what's the challenge? The challenge is that when you have a large grid, in CFD, we often solve a problem with a large computational grid. And our system is large as well, means that we have multiple solution variables. And then you also have a strong nonlinear relation in all the terms. So that comes to the problem that how are we going to scale it to the larger problem? As you can see, this decomposition and then will become larger, and this is the bound dimension. The bound dimension is basically indication of the computational efficiency. So how do we scale? We have this built-in adaptivity because we have AMR. We have we can do a little bit of efficient multi-resolution correlation. So this is critical in turbulence. It is offering profound information in our understanding of the energy transfer process across the different scales, space and time, and then nonlinear dynamics as well. So how do we address this? Now we develop a adaptive tensor network state. So adaptive tensor network state. We want to use graph edge covariance. Graph, that's where I mentioned earlier. So this, I highlighted the top part. This is my graph. So I want to use this graph help me to improve the computational efficiency when I have to solve a larger system, a more complex problem. And these edges, you can see I have solid lines, I have dashed lines. So for the solid lines, you can see that typically they are on the same resolution. The dashed lines is across different resolution. So how do I weight this? I want to build a graph. So the importance is I want to build a graph. And when I build this graph, and I want to use some information guiding me, I don't want to use the entire mesh. I don't want to compute all the relations between all these nodes, and I want to reduce the size of my graph. So the important refinement criteria is edge covariance. So edge covariance using two-point correlation. For example, if I have two-point correlation, I can compute all these, and then based on my, so I need an indicator. I am hearing my echoing. Is that okay now? Okay. So how do we really reduce the size? There's important quantity, edge covariance. And what are we based on? So there's so many quantities we can use. For example, I can use a Taylor microscale. If I use Taylor microscale, and then for turbulence, you know what this quantity is. Basically, if you have knowledge about the fluctuation, velocity fluctuations, you have viscosity, all this information. So we could really compute this based on some empirical relationship. This is your viscosity, this is your fluctuation, and then this is dissipation rate. So let's say this give us some thresholds, and then I can apply the knowledge to reduce this graph. This is one way to help me to solve, basically to simplify, reduce the bounded dimension, make the calculation a lot more efficient. Okay, so this is the part for decomposition, adaptive decomposition, and how do we do the scaling. So for next thing is that we want to evolve in time. So you have this PDEs, and after we discretize in space, we can get an ODE. After we get this semi-discrete ODE, we evolved in time. So you build this time-evolving MPO decomposition. So this is our circuits. So this is the MPO, that's the depth. And this is fine if you have a smaller problem, and then we can trotterize the delta T and then get our solution. And so the same problem for CFD, for high Reynolds number flow, particularly that's what we're interested in, and then this will become really long circuits. We don't want the depth too large. So we don't want it. How do we get around this problem? How do we get around the challenge of large circuit depths when solving the real world CFD problem? So we are interested in investigating the variable fast forwarding algorithm. So that's the VFF method. Variational fast forwarding algorithm. So essentially, what we can do is that maybe we can take this, approximate it by a diagonal factorization. So if I can approximate all that, and then I could just do a one shot. And I shouldn't say the word shot, means a different meaning in quantum computing. So I can one constant circuit depth, and I can get my solution. So that sounds really nice. And then instead of doing a long, many multiple steps, and then we could just do a constant circuit depth. But the challenge is the diagonalization. It's like every new method always comes with challenging, and then we have to find a new way to overcome the challenge. So here the challenge is diagonalizing this term here, and then it involves optimization. So when we optimize this process, and then you have to consider the high nonlinearity of the cost function and stochastic errors due to decoherence of qubits, control errors, readout errors. So the situation becomes even worse when multiple channels include in the optimization. So this is something that we are trying to explore. And lately, I've been working on multigrid reduction in time. So this is a very interesting technique, can help us speed up the optimization. So the multigrid reduction in time is typically we do multigrid in space. In CFD, we have done this quite a bit, but multigrid in time is very nice for elliptic problem, from optimization problem. So this is actually from my collaboration with Lawrence Livermore National Lab. They have a very good package that we have been working with to try to apply multigrid in time for high Reynolds number turbulence. And it also works really well with the adaptive mesh refinement, integrated them together. So potentially with that strategy, we can overcome the optimization problem. So this is something that in the next step exploring. So I will just quickly mention what's the follow-up work. And we will test this on the Burgess equation so that we can verify our nonlinear solver is working, and our approach gave us the accuracy and the efficiency. In the second problem will be the system equation with, so once we're representing, right now the focus on this one. So this is the core part, nonlinear term. So we know how to representing linear term already. And then we can, starting with the source term, just simple source term. And then this method is addressing this nonlinear term. So the next immediate work is focused on and testing these two problems. And I would like to do two things, mention quickly. Appreciate the NSF of supporting this work. I can devise the concept of algorithms, and also I have many constructive discussions with my colleague Mirali from Oak Ridge National Lab and Yu from Los Alamos National Laboratory. So I'm going to stop here so we can come back to some terms. If there's any questions, I think will be nice to discuss, and then we can also get your input, suggestions as well. Thank you very much for your attention. I look forward to your questions.